Think about the subtle creaks a wooden chair makes when you sit down, or maybe how a freshly polished surface gleams. It all hints at these forces at play, right? Often invisible stuff.
Exactly. Tiny stresses, surface-level interactions, they're fundamental to how pretty much everything around us behaves.
Okay, let's unpack this then, because this deep dive, we're venturing into the really intriguing world of solid electrode surfaces and what are called their electro-chemo-mechanical properties. Bit of a mouthful.
It is, but essentially we're exploring how applying electrical charge or, inducing chemical changes right at the circuit of a solid electrode, how that directly influences the physical forces acting there.
Okay.
It's this fascinating interplay, really, between the electrochemical environment and the mechanical state of the surface itself.
And you, our listener, you've actually provided some really compelling material on exactly this topic. So whether you're bumping into this in your professional field, maybe you're a student deep in material science, or maybe you're just curious about how materials work. Our goal today is to pull out the core insights from these, there's scientific sources, and make these complex ideas not just understandable, but hopefully genuinely captivating.
Yeah, and the material you've shared, it covers a pretty broad spectrum. We're talking fundamental thermodynamics governing these surfaces,
Right.
some really ingenious methods used to measure these tiny forces, and then a whole range of illustrative examples. We'll be looking at how surfaces can spontaneously rearrange themselves.
Oh, interesting.
How molecules stick on this really intriguing process called under-potential deposition, where atoms build up literally one layer at a time.
Wow.
The stresses that develop inside growing oxide films, and even the mechanical properties we can probe right down at the nanoscale.
So it really is interdisciplinary then. It's sitting right at the crossroads of electrochemistry, material science, maybe even a bit of physics in there.
Definitely. So our mission, as I see it, is to pinpoint the most crucial bits of knowledge, clarify the connections between these electrochemical and mechanical things, and, maybe even uncover some surprising twists or ongoing debates that keep researchers busy in this field.
Sounds good. So where should we start to sort of unravel this electrochemomechanical world?
Well, I think a logical starting point is always the foundations, right? Surface thermodynamics. It's really essential to recognize that the surface of a solid isn't just this abrupt end. It behaves more like a distinct region. You could call it an interphase, with properties that can be quite different from the bulk material underneath.
Okay, so a surface phase, almost like a special skin on the material with its own rules.
Yeah.
And within that skin, that surface phase, what's the key concept we really need to get our heads around?
For solid electrodes, the key thermodynamic parameter is surface stress. Now, it's really important to distinguish this from surface tension, which you might be more familiar with from liquids, like the surface of mercury. In liquids, the atoms are pretty mobile. They allow for what's called surface plastic strain. The surface can easily deform just by changing the number of atoms there. But in solids, where the atoms are, more locked in place, deformation also involves elastic strain. That's a change in the spacing between the existing surface atoms.
Okay, so if I'm picturing it, stretching a balloon is like the liquid you're just spreading the rubber.
Yeah.
But stretching a solid metal sheet, you're actually pulling the atoms further apart from each other. That's the elastic bit.
That's a great analogy. Exactly. And the Gibbs model, that gives us a framework for understanding this mathematically. It provides relationships that describe the excess energy sort of concentrated at the surface.
Okay.
And importantly, it introduces surface tension. That's usually the Greek letter gamma, which is associated with that plastic deformation in liquids.
Right, the balloon stretching.
And surface stress, usually denoted by G, which is linked to the elastic deformation we see in solids. The metal sheet stretching, those are really key terms to keep separate in your mind.
Got it. Gamma for flow and changing atom count. G for stretching or compressing the solid lattice itself.
You've got it. And this distinction, it becomes really clear when we look at something called the electrocapillary curve. That's basically a plot of surface stress or tension against the electrical potential applied to the electrode.
Okay.
For liquid electrodes, like mercury, you see this characteristic sort of parabolic shape. But for solid electrodes, like gold, experiments show results that deviate from that nice parabola. It confirms that, surface stress and surface tension really are distinct things in solid materials.
Interesting. So solid surfaces have their own unique mechanical reaction to electricity, unlike liquids. Okay, so how on earth do scientists actually measure these surface stresses? I mean, you can't exactly stick a tiny ruler on an atom, can you?
No, you've hit a major challenge there. Measuring the absolute value of surface stress is incredibly difficult.
Right.
However, what we can do, and quite precisely, is measure changes in surface stress, and we use some very clever techniques for that.
Okay.
Well, one method is piezoelectric detection. The basic idea is that when the surface of a piezoelectric material experiences a change in stress, it actually generates an electrical signal. This leads to concepts like eastance, that's the change in surface stress with respect to potential, and quiescence, which is the change in stress with respect to surface charge density. And there's something called the Gokhshtein equation that provides the theoretical link between these electrical signals and the changes in the surface stress. It essentially gives us the mathematical connection.
So a tiny mechanical tweak on the surface makes a measurable electrical current. That's pretty elegant, actually. A neat way to probe these forces.
It is. But calibrating these measurements accurately, figuring out the exact conversion factor, often called K, between the signal and the stress change, that can be tricky.
I bet.
So researchers often use combined measurements. They'll measure the piezoelectric signal and the surface charge density together to try and nail down that calibration. It's outlined in some of the equations in your sources, actually.
Okay, so electricity gives us an indirect read. What about methods that, more directly measure the mechanical response, the actual bending or stretching?
Yeah, the cantilever bending method is probably the most common and, relatively speaking, straightforward approach. Imagine a microscopic diving board that's your cantilever.
Okay.
The solid electrode material is often put down as a thin film on this tiny diving board. Now, when the surface stress on that electrode film changes, maybe because you applied a potential or a chemical reaction happen, it causes the whole cantilever to bend, either up or down. It's a bit like a bimetallic strip bending with temperature changes, but here it's reacting to electrochemical forces.
Like a tiny electrochemically sensitive seesaw. Got it. How do we then measure that minuscule bend? It must be tiny.
Oh, it is. Typically, we use optical detection with laser beams. You shine a laser onto the cantilever surface, which acts like a little mirror. As the cantilever bends, the reflected laser beam changes its angle, and this change in position is picked up by a sensor. By measuring that deflection angle really precisely, we can calculate the curvature of the cantilever and, from that, work out the change in surface stress.
So a tiny bend shifts a laser spot. And we can measure that shift very accurately.
Exactly. But there's always a but in experiments.
Yeah.
When we're doing this in an electrochemical cell, we have to remember the electrolyte solution and the optical window the laser passes through. Light bends when it goes from one medium to another. That's refraction.
Right. Physics gets in the way.
It does. So refraction can introduce errors. You need to use corrected formulas that actually account for the refractive index of the solution to get accurate stress measurements.
You can't just ignore the messy reality of the environment the electrode's sitting in.
You really can't. And then finally, if we want to see how surface stress changes over time, researchers use something called dynamic stress analysis, often paired with electrochemical impedance spectroscopy, or EIS.
Okay, what does that involve?
Basically, you apply a small oscillating electrical potential to the electrode, and you analyze the resulting wiggles, the oscillations in both the electrical current and the surface stress.
Right.
By looking at how the stress response relates to the potential input, things like amplitude and phase shift, you can get insights into the kinetics, the speed of the processes affecting surface stress.
So we're not just taking static snapshots, but watching how these forces evolve in real time as we tweak the electrical conditions. Okay, that gives us a really good handle on how these invisible forces are actually measured. Let's dig into some concrete examples now. Where should we start seeing these electro-chemo-mechanical properties in action?
Okay, good idea. Having grasped the basics and the measurement techniques, let's look at some real-world examples that really illustrate this interconnected dance between electrochemistry and mechanics we talked about.
Perfect.
Let's start with gold surfaces. They show some fascinating behavior, specifically phenomena called surface reconstruction and adsorption.
Okay, gold. What happens there?
Well, if you take a really pristine metal surface, like gold with a specific crystal orientation, say 111, and prepare it in a vacuum, the surface atoms often spontaneously rearrange themselves. They do this to minimize their surface energy. This is called surface reconstruction. It can involve forming these intricate 2D patterns or superlattices that are different from the atom arrangement deeper in the bulk material.
So the very top layer of atoms just decides, nope, we're organizing differently up here just to get into a lower energy state, like tidying a room to make it feel calmer.
That's a perfect analogy, exactly like that. Now bring this into an electrochemical setting. Applying an electrical potential or just letting ions from the electrolyte solution stick onto the surface, that can actually trigger transitions between these reconstructed and unreconstructed states.
Really?
Yeah, for example, on gold, 111, in perchloric acid, that reconstructed state lifts, it disappears. Around -0.2 volts relative to a standard reference electrode, SEE. And this transition, it comes with significant changes in surface stress.
Wow. So just by tweaking the electrical environment, we can basically tell the surface atoms, okay, go back to normal, or adopt this new pattern. And those tiny atomic shifts have a real mechanical effect, changing the overall stress.
Precisely. And when we compare how surface stress changes with potential to those traditional electrocapillary curves for gold, the experimental data clearly shows that surface stress and surface tension are different beasts for this solid.
Okay, proof in the pudding.
Exactly. And furthermore, we can define these coefficients, like the surface stress surface charge coefficient, DIG-Q, and the potential surface elastic strain coefficient. Theoretically, these two should actually be equivalent.
Two different ways of measuring the electrical effect on mechanics.
Kinda, yeah. And experiments on thin gold, 111 films in perchloric acid, have pretty much confirmed this theoretical equivalence. They line up.
Okay, so the theory holds up in practice there. That's good.
It does, although interestingly, for some materials like nanoporous gold or maybe platinum electrodes, we sometimes see a reversal in the sign of these coefficients.
A reversal? What does that mean?
It suggests that the unique electronic structure of these very high surface area materials plays a really critical role in how they respond mechanically to electrical changes.
So the actual physical shape of the surface flat plane versus spongy network can dramatically change how it behaves.
Absolutely. Let's take another specific example. Iodine adsorption on gold, 111. Experiments show a nice linear relationship between the change in surface stress and the surface elastic strain caused by that layer of iodine atoms sticking on.
Okay.
And this linear relationship actually lets us estimate mechanical properties of the adsorbed layer itself, like its two-dimensional elastic modulus.
Whoa, hang on. So we're not just seeing a change in the gold stress, but we can use that change to figure out how stretchy or stiff the iodine layer is. That's powerful.
It is indeed. It gives you a window into the mechanics of these ultra-thin layers.
Okay, that's fascinating. What's another compelling example?
Another really interesting area is under potential deposition, or UPD.
UPD.
This is a process where we deposit a very thin layer, often just a single layer of atoms, a monolayer of one metal, onto the surface of a different metal substrate. And the key thing is, it happens at electrical potentials that are more positive than what you normally need to deposit the bulk metal.
So it's like you're tricking metal A into plating onto metal B before the normal conditions are met. How does that work?
The main driving force is the interaction energy. The atoms of the deposited metal often bind more strongly to the substrate atoms than they do to each other in their own bulk material.
Ah, okay. They prefer sticking to the other metal.
Exactly. And empirically, the potential window where UPD happens is often related to the difference in work functions between the two metals. Work function being basically how easy it is to pull an electron off the surface.
So the sort of electronic stickiness of the metals dictates how easily UPD occurs.
You've got it. And the equilibrium potential for UPD, the point where a certain amount is stable on the surface, that follows adsorption isotherms, much like gas adsorption.
Yeah.
You can even use models like the Langmuir isotherm to describe it.
And I'm guessing adding this new layer of atoms is going to mess with the surface stress of the substrate, right?
Oh, absolutely. A classic example is lead, PB, UPD on gold. 111. Lead atoms are quite a bit larger than gold atoms.
Right.
So initially, as lead atoms adsorb, they tend to induce compressive stress. They're sort of squeezing the gold surface.
Makes sense. Bigger atoms trying to fit.
Yeah. And as you deposit more lead, it can form ordered monolayers, like a hexagonal close-packed structure. And it can even form surface alloys where lead atoms actually get incorporated into the gold surface lattice.
Mixing in.
And that alloy formation typically leads to additional compressive stress.
So first a squeeze from the lead sitting on top, then an even bigger squeeze as they mix in.
That's the picture. And we can even model this UPD monolayer as if it were a tiny freestanding elastic film. Relate the stress change to its elastic properties, like its biaxial modulus.
And what do you find?
Well, interestingly, for that hexagonal lead monolayer on gold, the calculated biaxial modulus is surprisingly close to the modulus of bulk lead.
Wow, really? A
Yeah.
single layer of atoms behaving mechanically almost like a big chunk of lead.
Yeah.
It's unexpected.
It is rather surprising, isn't it?
Yeah. So that's lead on gold. What happens if you try depositing, say, bismuth on gold instead? Does it behave the same way?
Good question. Bismuth by UPD on gold 111 is different. Unlike lead, bismuth doesn't really form surface alloys readily with gold.
Okay.
Instead, it forms its own distinct structural phases on the surface. And the stress changes reveal something called uniaxial electrocompressive stress.
Uniaxial, meaning?
Meaning that compression is mainly oriented in one particular direction along the surface, not equally in all directions like the lead case.
So different metals, even as these ultra-thin layers, leave their own unique mechanical fingerprint based on how they interact and arrange themselves.
Precisely. And it gets even more complex. Copper, CuPd on gold, 111, brings in another factor. Coadsorption of ions from the electrolyte, like chloride or sulfate.
The solution matters too.
It really does. Sulfate ion adsorption, for example, can lead to a decrease in stress, making it more compressive, possibly because the sulfate ions form little surface dipoles.
So it's not just the metal atoms, but everything in that electrochemical environment that can tweak these surface forces.
Absolutely. And even just the mismatch in the size of the crystal lattices between the deposited metal and the substrate, like with palladium, gold 111, that contributes to the stress too. Although sometimes the theoretical calculations based just on lattice mismatch don't perfectly match the experiments, which tells us other factors are still playing a role we need to understand better.
These UKD examples really drive home how intricate this all is. The electrochemistry and the mechanics are just completely intertwined at the atomic level. Now, you mentioned surface alloying earlier with the lead example. Can we delve into that a bit more? How does that fit in?
Sure. Surface alloying, like we saw with lead on gold, is the formation of an alloy that's basically confined just to the outermost atomic layers.
Right.
What's really intriguing is that these surface alloys can form even between metals that don't mix in their bulk forms. They might be immiscible normally.
So you could make a chunk of this alloy, but right at the surface, their atoms can mingle, like a very exclusive club only existing at the interface.
That's a great way to put it. And studies using techniques like ion scattering have found something interesting. In surface alloys, where the deposited atoms are larger than the substrate atoms.
Like lead on gold.
Exactly. The amount of surface rumpling, that's sort of the vertical displacement, how bumpy the surface is often less than you'd predict if you just treated the atoms like hard spheres bumping into each other. It suggests that the effective size, the radius of those larger adsorbate atoms, actually gets a bit smaller when they form the surface alloy.
So they kind of shrink a bit to fit in better with the substrate lattice. And that shrinking must affect the stress, I'd guess.
It certainly does. Generally, larger atoms cause compressive stress, right? If their effective size shrinks during alloying, that can partially relieve some of that compressive stress. We see evidence for this in systems like lead and tin on nickel electrodes. The measured distances between atoms in the surface alloy are shorter than simple hard sphere models predict.
Okay.
But conversely, if the adsorbate atom is smaller than the substrate atom, like copper on tungsten surface alloying, can actually increase tensile stress, pulling things apart more.
So it really depends on the relative sizes and how they accommodate each other at that interface, whether alloying squeezes more or pulls more.
Okay, what about processes where we're not just adding a thin layer, but actually growing a whole new material on the surface, like those anodic oxide films you mentioned? Yes, anodic oxides. That's another critical area where these electrochemo-mechanical effects are huge. When we anodically oxidize certain metals, often called valve metals, like aluminum, titanium, we grow a layer of oxide on their surface. And this film growth is almost always accompanied by the generation of internal stress within that growing oxide film.
That makes intuitive sense.
Yeah.
You're changing the metal into a new chemical compound, different volume, different structure.
Sure.
There's bound to be some mechanical strain, some stress building up.
Exactly. And several factors contribute to this stress. A key one is just the volume change from the reaction itself. There's something called the Pilling-Bedworth ratio.
Right, I've heard of that.
Yeah, it basically compares the volume of the metal consumed to the volume of the oxide formed. That volume difference is a major stress source.
Okay.
But other things matter too. How ions move through the growing film, electrostriction, that strain caused by this strong electric field during anodization.
The field itself causes strain.
It can, yeah. Also, crystallization within the oxide. and even things like oxygen gas bubbling off the surface can contribute.
Wow, so it's a real complex mix. Chemical change, particles moving, electrical forces, structural changes, all feeding into the stress in that growing layer.
It really is. There's a high field model that helps us understand the kinetics, how fast these films grow. Now, if we look at aluminum anodization, for instance, the stress in the oxide can actually flip from being compressive at low current densities to being tensile at higher current densities.
Really, it flips?
Yeah, and that shift often correlates with changes in the film structure, maybe going from crystalline to amorphous, and also depends on which ions are moving faster through the oxide.
So how fast you grow it and what its internal structure looks like drastically changes whether it's pushing in or pulling out.
Absolutely. Now, titanium anodization is another interesting case. We usually see an overall compressive stress in the titanium dioxide film that forms.
Okay, mostly compressive for T.
Mostly. But what's really curious is that even when the oxide crystallizes into a specific phase called anatase, which you might expect to cause tensile stress because it involves a slight volume contraction,
Right.
we often still measure significant compressive stress.
That seems contradictory.
It does, doesn't it? It suggests that other stress-generating mechanisms are dominant, maybe how oxygen atoms get incorporated during growth, or just the fundamental growth process itself creates more compression than the crystallization relieves.
Oh, yeah.
And if you do in situ stress measurements during titanium anodization, you see this complex evolution. There are reversible stress components, probably from that electrorestriction effect.
Right, the field effect.
And irreversible components directly linked to the film actually growing thicker. We even have to consider something called Maxwell stress, which is stress arising purely from the electric field within the oxide film itself.
Goodness. It's amazing how these seemingly simple processes, like growing an oxide, involve such a complicated interplay of forces right down at the nanometer scale. Okay, shifting gears again slightly. What about actually poking these surfaces to see how strong they are? Directly probing the mechanical properties at the nanoscale.
Now you're talking about nano-indentation. It's a really powerful technique for doing just that. It lets us investigate things like hardness and elastic modulus right down in the nanometer range.
How does it work?
Basically, you take a very sharp, very hard tip, often diamond, and you press it into the surface with a precisely controlled force while simultaneously measuring how deep the tip goes.
So like a tiny, incredibly precise hardness test.
Exactly. You're performing a mechanical touch test at a minuscule scale.
Okay.
And one key thing that comes out of nano-indentation studies is the indentation size effect, or IS.
What's that?
It's the observation that the hardness you measure at the nanoscale can actually be different, often higher than the hardness you'd measure for the same material at larger micrometer scales.
Wait, really? So a tiny bit of material can seem harder than a bigger chunk of the exact same stuff?
Weird, isn't it? But yeah, it highlights that mechanical properties themselves can depend on size when you get down to these really small dimensions.
That's fascinating. Why does that happen?
Well, one model, the Nix-Gao model, explains it by considering dislocations, tiny defects in the crystal structure. When you indent at the nanoscale, the sharp strain gradient under the tip forces the creation of extra dislocations called geometrically necessary dislocations.
Right.
And these extra dislocations make it harder for the material to deform plastically, hence the higher measured hardness at smaller depths. We see this effect in materials like magnesium oxide, for example.
So the very act of indenting at that small scale changes the material's defect structure right under the tip, making it seem harder.
That's the idea.
Okay.
And nano-indentation isn't just for simple materials. We can use it on pristine single crystal gold, carefully prepared without any oxide, to get the intrinsic properties of the metal surface. We can use it on those metal oxides we talked about, like TiO2 and magnetite, to get actual numbers for their nanoscale hardness and elastic modulus. For instance, doping TiO2 with niobium can make the hardness pretty constant over a range of indentation depths.
So you get direct numbers for how resistant these oxide surfaces are to being deformed.
Exactly. And it's been used on passive metal surfaces too, like iron sitting in a borate solution, which forms a very thin, protective passive film. Those studies show that even an extremely thin passive film, just nanometers thick, can significantly influence the measured hardness.
Wow.
Mhm.
A film that thin makes a difference you can measure.
Definitely. And you can even see the effect of surface treatments. For example, putting a chromic conversion coating on passive iron changes its nanomechanical properties in something called the work ratio, which relates how much the deformation is elastic versus plastic.
It's incredible how much influence such a tiny layer can have on the overall mechanical feel of the surface. Now, you mentioned earlier there are still some debates bubbling away in this field, especially around the thermodynamics. What are the sticking points there?
Yes, that's right. The surface thermodynamics of solid electrodes, particularly that fundamental relationship between surface stress, G, and surface tension, has actually been a topic of considerable and quite long-running debate in the scientific community.
Ah, okay.
Yeah.
We touched on that distinction early on, stress for solids, tension for liquids, but it's still debated.
The precise thermodynamic relationship for solids is, yes, it's more complex because of that elastic strain component in the solid lattice.
Right. So where's the actual disagreement?
Well, one key point of contention is around the Gibbs-Duhem equation when applied to solid surfaces. The sort of standard version, derived using certain assumptions, doesn't explicitly include a term for elastic strain, but a more generalized form, put forward by researchers like Couchman and Davidson, does include this elastic strain term. This difference in the fundamental equations leads to big discussions about the correct thermodynamic way to treat solid surfaces.
So it's a disagreement right down at the level of the basic math used to describe these systems.
Pretty much. And then there's the Shuttleworth equation. This equation tries to explicitly relate surface stress, G, to surface tension, and how surface tension changes with strain.
Okay, sounds important.
It is, but its validity has been fiercely debated. Some researchers, like Bottomley and colleagues, argue that the way Shuttleworth derived it is actually inconsistent with Hermann's formulation of thermodynamics, which is a very rigorous mathematical framework for the whole field.
Whoa.
Yeah, they basically suggested that if Hermann's theory is right, the Shuttleworth equation must be wrong.
That's a pretty bold claim against a seemingly established equation. So a fundamental theoretical disagreement.
Indeed. Now, others, like Ericsson, Rusinoff, and Eibach, have defended the Shuttleworth equation, offering alternative derivations or interpretations. But the debate has lingered.
Why hasn't been settled?
A major hurdle is actually experimentally verifying the Shuttleworth equation directly. It's proven extremely difficult to do definitively. Plus, there are ongoing thermodynamic questions about how best to apply it to electrified solid electrodes and how to interpret those cantilever bending measurements we discussed, specifically around whether you're keeping elastic strain constant or electrode potential constant during the measurement and how that affects the thermodynamic analysis.
So even in what seems like established science, there are still these fundamental questions and lively debates right at the cutting edge. It really shows how much we're still figuring out about how materials behave right at their surfaces.
Absolutely. These controversies really underscore the continuous effort needed to build a fully comprehensive and self-consistent thermodynamic picture for solid surfaces, especially when they're sitting in a complex electrochemical environment.
Well, this has been a truly deep dive, hasn't it, into these electrochemo-mechanical properties of solid electrode surfaces. Let's just quickly recap some of the key things we've pulled out.
Sounds good.
We've definitely learned about that crucial difference between surface stress in solids and surface tension in liquids. That elasticity matters for solids.
Right.
We looked at the really clever ways scientists measure these subtle forces using electrical signals from piezoelectricity, watching tiny cantilevers bend with lasers, even poking surfaces with nano-indenters.
Measuring the changes.
Exactly. And we explored some great examples how gold surfaces reconstruct, how molecules absorbing change stress, that fascinating underpotential deposition process,
Building atomic layers.
and how stresses build up in growing oxide films, all showing how electrochemistry directly impacts mechanics at the nanoscale.
And we also touched on surface alloying, that mixing right at the interface with its own mechanical signature, and, of course, these ongoing scientific discussions about the fundamental thermodynamics reminding us that science is always evolving, always questioning.
Yeah, there were definitely some aha moments for me, like the idea that a single atomic layer in UPD could behave mechanically almost like the bulk material. That was surprising.
It is counterintuitive, isn't it?
Totally. And the complexity of stress in oxide films, or that whole debate about surface stress versus tension,
Yeah.
it really highlights the depth here.
And understanding all this isn't just academic curiosity, is it? It has real practical implications. Think about catalysis, corrosion prevention, thin film technology for electronics, designing new materials.
Right. Optimizing reactions, stopping rust, making better devices.
Exactly. This fundamental understanding is crucial for advancing those technologies.
So all this deep science really does connect to things that affect us every day. It really makes you wonder, thinking about this incredibly intricate dance of forces right at the atomic level, what completely new materials or technologies might pop out if we get an even deeper grasp of these electrochemomechanical properties.
That's the exciting question, isn't it?
And the fact that even fundamental thermodynamic relationships are still debated, it suggests how much we still have to learn about matter right at its boundaries. What other areas of science that seem settled might actually hold similar hidden complexities, just waiting for us to find them.
It's a great point, and hopefully, if you, our listener, found this deep dive into the electrochemomechanical world as fascinating as we did, we really encourage you to explore the sources we've been discussing and maybe dig even deeper into the research. It's a truly captivating and constantly evolving field.